Hi, Matt Roscoe here at the University of Montana with a lecture on analytic geometry and measurement for our course Math 573 Geometry for Teachers. Today I'd like to talk to you a little bit about these two areas, analytic geometry and measurement. Both of these are gigantic topics, and of course we could spend a whole course on either. So we're just going to delve into mostly a few examples, examples that might take elements from the K-12 curriculum and apply them in sort of a more robust manner, something to deepen our understanding of analytic geometry a bit. Um, in analytic geometry, those examples will be built most upon the distance formula and slope and its implications on lines. Um, and then I'd like to just briefly talk about measurement, which is closely related to analytic geometry. It's this idea that there's a unit by which distance is measured, which provides then for both area and volume as well. So we'll do a few measurement examples, and I want to show you at the end how you could use GeoGebra to support measurement concepts for your students. Okay, so let's get into the analytic geometry half. Analytic geometry is sometimes called Cartesian geometry or coordinate geometry, and it's the study of shape drawn on the coordinate system. The Cartesian, just so you know this, it's named after Descartes, and he was the one who came up with the what we think of as the Cartesian plane, and that's borne out by the fact that I guess the imprints of that fact is on the letter M chosen for slope, which is the French verb monter, to climb. Okay, so in analytic geometry, like one thing that you probably teach or have at least seen in your mathematics career or helping students get ready for or apply is the distance formula. If we have 2 points on the plane, then the distance between 2 points on the plane is given by this complicated formula, square root of x2 minus x1 plus quantity y2 minus y1 squared. Sometimes this is given this way, absolute values. The reason this doesn't make it doesn't matter if it's either positive or negative, of course, is because of the squaring. It's going to get rid of any negatives. Um, Sometimes we see it this is those differences in x's called delta x's and differences in y's called delta y's. Um, but if we, I guess, undo the square root, if we square both sides, this is what we see. And of course, this is where the formula comes from. I hope that you recognize that that looks vaguely familiar to, a square being equal to the addition of two other squares, which is, of course, the formula template for Pythagoras. So really all that's going on here is we're taking a slanted distance, a distance that we could think of as a hypotenuse, and we're saying that its distance squared has to be equal to the horizontal and vertical distances, so the changes in x and the changes in y's squared and added together. So all the distance formula is an instantiation of the Pythagorean theorem, of course. And that's the way it's usually derived in the courses where it's introduced. So just a quick romp through the distance formula. Let's talk about slope briefly. Suppose that a line passes through points x1, y1, and x2, y2 on the coordinate plane, then the slope m of the line is defined as rise over run. So in words, we sort of think of it as rise over run, which is the change in y over the change in x, which is, I guess, from the second point to the first would be the y value of the second point minus the y value of the first point over the x value of the second point minus the x value of the first point. So y2 minus y1 over x2 minus x1. This is a common, topic that's introduced usually in 8th grade and then follows us all the way through calculus. Is perhaps one of the most important, I guess, measurement concepts from analytic geometry that runs throughout, our study of algebra and on into, it becomes really principally important in calculus, where we're studying the rate of change of functions, which has to do with how the slope of curved functions are changing. So some implications, horizontal lines have slope equal to 0. That's because we have no rise over some run. Vertical lines have a slope that's undefined. That's because we have rise divided by no run, by 0 run, and we can't divide by 0. But as a line approaches vertical, that is, as it gets nearer and nearer to vertical, its slope gets larger and larger and approaches infinity. And then two lines with slopes that are negative reciprocals are perpendicular. So For example, a line with slope 3/4 and a line with slope 4/3, -4/3 would be perpendicular. The way you can kind of think about this is that, if a line is perpendicular to another line, we can think of it as being rotated by 90 degrees about the origin. So if you rotate a line 90 degrees about the origin, it's basically its rise becomes its run, and its run becomes its rise, right? And its direction, if it's rising, becomes falling, and vice versa. So this negative reciprocal relationship can be explained through rotation or appeal to transformational geometry, really. And then the last thing is, it turns out that the equation of a line can be derived from the slope equation, and I won't do that here. Some of you have probably done that before, but that's where it comes from. It's from the definition of slope, and the most common form of it in high school, at least, is this slope-intercept form of the line. So it's the form y = mx + b, where b is the y-intercept of the line. So hopefully these are things that are familiar to you. Let's move on and do some examples and see if we can apply some of this to some, let's say, some moderately difficult problems. So let's say we have this triangle. A, B, and C are points on the plane at 8, -8, 4, 4, -4, and C is 10, 5. And we're going to classify this triangle as either right, obtuse, or acute, and then also classify it as either scalene, isosceles, or equilateral, and we're going to use an analytic approach to do so. All right, let's go ahead and dive in. So I have here at the ElmoCam a picture of the triangle. At first glance, it really looks like the triangle is a right triangle, but it's hard to tell if for certain that angle is a right triangle or a right angle. Perhaps it could be, or perhaps it could be 89.5 and this thing is actually acute. So we're going to use an analytic approach to try to figure out what what type of triangle we have here. So let's go ahead and start it by finding the distances for each one of these lengths of sides. That'll tell us if we have an isosceles, equilateral, or scalene triangle. It sure appears to be scalene. It doesn't appear that any of the distances are the same, but let's just confirm that. So let's do AB first. If I want to go from A to B, then I take the square root of the changes in the x's and the changes in the y's and sum them, or sum the changes in the x's squared and the changes in the y squared and square root it. Sorry. So here's the distance formula played out there. Let's see, it'd be 4 minus -8 quantity squared plus, let's see, -4 minus 4 quantity squared. That answer all square rooted. Let's see, so we'd have 12 squared, that'd be 144, plus 16 squared, sorry, 8 squared, that'd be 64. So here we get the square root of 208. This is this distance from A to B. I just want to make sure that you understand that these are real distances, right? If I take the square root of 208, my calculator, I get 14.42. So I'll just sort of put that off to the side. And it's roughly, right? This is an irrational number. But now you could come up here and you could put your compass on that distance, and once you have that distance on your compass, you should be able to then find, let's see, where's a good place to put it. There we go. So that's that distance to there, and of course this, if I carried this out, that would be -15. So it does look like it's sort of 14 and change. 14 is right here for me on that picture. So I think this is an important thing to do for kids whenever you do this kind of, teach this kind of thing, is to show them that that's indeed a number. It's just a decimal number, and it can be compared to lengths on the x and y axis to see if it seems to be correct. Let's see, so we've got AB. How about BC next? we would expect a number smaller than the square root of 208 there. Let's see if we get it. 4 minus 10 quantity squared plus negative 4 minus 5 quantity squared, all square rooted. So we get negative 6 squared, that would be 36 here. And we get negative 9 squared, that'd be 81 here. Let's square root that and call it 117 square root. If I sort of check it on the calculator, I get about 10.81. And let's see, A, B, B, C. The last one is CA. CA is going to be, let's see, 10 minus a negative 8 quantity squared plus 5 minus 4 quantity squared, all square rooted. So 10 minus a negative 8, that's 18 squared. What is 18 squared again? 324 plus 1 square rooted, so that's the square root of 325. Okay, so, and yeah, what is that, I guess, roughly? 325 square rooted, so square root 325, 18.2, really close to 18. Yeah, it would be interesting to just check it and see. I guess it makes sense because these two guys are separated by 18, but it goes down 1 and over 18, so it's got a little bit more than 18. I mean, if I just put it on 10 and run it out here, I can see that 5, 10, 15, yep, 18-ish, right where it's at. So appears to be correct. And we can say from this that triangle ABC is scalene. And the reason is because no sides are equal, so the way that I'll put that is I'll say CA is greater than, what's the next one, AB, which is greater than BC. And it's strictly greater, not equal. So we definitely have a scalene triangle. The next thing to check is to see if we have a right triangle or an acute or obtuse triangle. So one thing to check for rightness that you could do right here is you could check, you know, the slopes of these lines and see if they're negative reciprocals. So I'm going to try to find the slope of AB and the slope of BC. So that's going to be, let's do AB first. So AB, let's go from A to B. So this is y2, x2, y2, this is x1, y1. So that's going to be the rise over the run going from A to B. So let's see, rise is going to be the y's, so it'll be negative 4 minus, let's see, positive 4 all over 4, which is the x coordinate for B, minus the x coordinate for A, which is negative 8. So let's see what we get. We get negative 8 on top, and we get 12 on bottom. So it's negative divided by 4 on both sides. Let's see, so it would be negative 2/3. So that means that I should be able to go down 2 and over 3 and get back. Yep, I can. Down 2, over 3 and get back. Down 2, over 3 and get back. Down 2 and over 3 and get back. And what's kind of neat is the simplification. The 4 that I took out here are these 4 iterations of 2/3 as the slope. So you can kind of see how the number theory actually works out in simplifying how much I went down and how much I went over in getting from A to B. So it's sort of like this. Okay, so I believe that, negative 2/3. And the question now is, what's the slope of BC? Again, it's rise over run. So I'm going to go from B to C, so that means this is x1, y1. Oops, I'm a little bit off the page, the screen, sorry. So this is x1, y1, that's x2, y2. And let's do it. So y2 minus y1 would be negative 4 minus 5. x2 minus x1 would be 4 minus 10. So we get a we get a negative 9 on top. We get a negative 6 on bottom, which is going to simplify to first positive over positive, and then 3's are in there. So it looks like 3 3's on top, 2 3's on bottom. And indeed, we have negative reciprocals indicating that that is a right angle. Let's just make sure that everybody understands what's going on here as far as the picture goes. Let's move our label for B to 4 comma negative 4. So in going from from C to B, I go down this many and I go back this many. That's 9 and that's 6. But apparently there were 3 of them in there, each a 3 and a 2. So we could go down 3 over 2, down 3 over 2, down 3, and over 2. So something like this is what the simplification did. It simplified down 9 over 6 into 3. Could be considered down and down, right? Down 3 over 2, down 3 over 2, down 3 over 2. But of course that could be written as over 2 up 3, over 2 up 3, over 2 up 3, over 6 and up 9. So anyway, that's the idea. So triangle ABC is right because the slopes of AB and BC are negative reciprocals. Here's an aside. Perhaps you noticed as we went through here on the first page that there was maybe an easier way to tell what kind of triangle we had by using the converse of the Pythagorean theorem. And the converse of the theorem says that if a squared plus b squared equals c squared for any triangle with side lengths a, b, and c, then that triangle is right. So you can use it to prove rightness if the formula indeed works. And I guess you can kind of see that 208 and 117 when added together make 325. So an aside would be that square root of 208 squared plus the square root of 117 squared is going to be equal to 208 plus 117, right, which is equal to 325, which is the same thing as square root of 325 squared. So indeed a squared plus b, these are the lengths, right? The lengths of the side, length of a side, length of a side. Since they work in the Pythagorean theorem, therefore triangle ABC is right by the converse of Pythagorean theorem. I hope that makes sense. Just a different way we could have done that without having to calculate slope up here. I particularly like this one because it also tells you whether when this doesn't work, whether your hypotenuse is too long or too short. So that it tells you whether or not you have an obtuse or an acute triangle when it's not right. In other words, had this been had this added together to be 324, we would have known that the hypotenuse was too long to be right, and if it's too long to be right, it must be obtuse. Okay, well, just one example there of some synthetic geometry at play. Excuse me, some analytic geometry at play. Let's take a look at another problem. But perhaps before we do that, maybe I should just check this one really quick using GeoGebra. One of the things that GeoGebra makes really easy is checking these analytic problems because, of course, everything you construct is on the coordinate plane to begin with. So one thing you might not know about GeoGebra is that down here at the bottom left, there's this thing called the input bar where you can just type in things. So I'm just going to type in -8 comma 4 in parenthetical form, and it'll throw up a point there. I'm going to type in 10 comma 5, and it'll throw up another point. And then I guess I would type in 4 -4, and there's my triangle. There it is. Here's the segment length, so we can see right away, just based on the lengths of the segments, that this is a scalene triangle. And then if you just choose the angle measurement tool and tap on the triangle, you can see that indeed that angle in the right in that corner is 90. So it's kind of neat there. You can quickly check things on GeoGebra, especially analytic problems in geometry. Check out really quickly. Okay, let's move on to another example. So let's find the equation of the locus of points that are all 4 units away from the point 3, -5 using an analytic approach. So in this particular problem, we're after an equation, so some relationship between x and y, and we're looking for this collection of points all 4 units away from 3, -5. Okay, so I'll switch over to my Elmo cam here and take a look. Huh. There it goes. Just didn't update. Okay, so I have the picture drawn. Here's the point 3 comma -5, and we can see that this would be the collection of points that are all 4 units away from 3, -5, and of course what we're after here is the equation of a circle. And you may or may not have seen this before, but it turns out that again the equations for lots of things that we know about on the coordinate plane come from these real basic things, like the equation of the line comes from our notion of slope, and it turns out that the equation for a circle comes from our notion of distance. So here's the idea. The idea is that what I want is I want a relationship between x and y, any x and y on this circle. So I'm going to just leave it as a variable, x and y, such that this point x and y, x comma y, is 4 units away from this point 3 comma -5. So what that means is if we just sort of take the distance between these 2 points, then we know that the difference between x and 3, quantity squared, plus the difference between y and -5, quantity squared, has to be equal to, I guess the square root of that would be the distance 4. So this is just the distance formula. But if we wanted to simplify this, the way that we usually see this in the equation of circles, we just square both sides, and we'll get x minus 3 squared plus y minus a -5, quantity squared equals 4 squared, or 16. But this is this is the, I guess, the equation that is generalized. So generally, if h comma, let's call it h comma k, is the center of a circle of radius r, then the equation of the circle is what? Well, it's x minus h, quantity squared. You can see that here in the x minus 3, where 3 is the coordinate of the x coordinate of the center, plus y minus k, quantity squared. And again, this y minus a -5, the -5, of course, is built in the coordinate there, but the minus is built into, I guess, the form of the formula. And that's going to be equal to r squared. So this is just a generalization of the equation that we found for the circle up above. So that's kind of neat, with The equation of a circle is just a generalization of the distance formula for a generic point on a circle. All right, well, that's kind of interesting. Call that example 2. And then my example 3 builds on this example. Maybe we should just check this quickly in GeoGebra just to show you that you can do this also nicely with the input bar. In the input bar in GeoGebra, you can type in any equation and it'll graph it for you. So down here in the input bar, all I'm going to put in is what x minus 3 quantity squared plus y minus negative 5 quantity squared equals 4 quantity squared. And there it is. I'll hit enter, and it adds this circle to the circle. Does appear to be a circle centered at 3 comma negative 5, so I'll put that there with a radius of 4, right? Yep, there it is. Just to check it for sure, we could put a segment on there and measure the distance if we wanted to. Just make sure that's radius 4. Yes, it is. And if I move the point around, of course, all those points are 4 units away from the center, and checks out. Okay, let's go ahead and take a look at our last example from analytic geometry for today. A little bit more involved one. A line with slope 3/2 is tangent to a circle with radius 4 and a center 3, negative 5. Find the point of intersection of the line and the circle. There may be more than one solution. Okay, so let's just read it again. Slope's 3/2 and it's tangent to a circle radius 4, center 3, negative 5. Find the point of intersection of the line and the circle. Okay, let's attack this one. All right. So there it is, the circle from our last problem. But now the question is, what about a line with slope 3/2? How would it interact, I guess, with this circle? And where would it touch the circle? Just barely touch it without actually passing through. So what I'm going to do is just start with a line with slope 3/2. So I'll come up here 3 and over 2. And I'll just draw in a faint line just to give you a sense of what we're talking about. Okay, so there's a line with slope 3/2. It doesn't touch the circle, so it's not tangent to the circle. But if I moved it over just a little bit, like say about right there, I can see that that would be a line with, approximately slope 3/2 touching the circle. I'm just sort of roughly estimating this with this line that I've drawn. I'll draw another one in here. That one touches the circle, but it's not tangent to it. But if I come back here and say about right there, there's another line with slope 3/2. So just to make it completely clear, these lines all have this slope 3/2, right? So they're all 3/2. And the question is, what are the coordinates of these 2 points of intersection? And it seems like, well, this is a fairly difficult analytic problem. It doesn't look like they touch at a very nice spot. If I'm kind of looking at lattice points, I guess, or integer points, it seems like this one's sort of in between. Well, it's close to 7, but a little bit less than 7 negative, and sort of, out here close to 7 positive too. This guy's sort of down -2 and back less than a half. But the question is, how would I analytically find those 2 points? One thing I notice is that, these 2 points seem diametrically opposed, and that seems to make good sense, right? If we kind of consider this line, that seems to be a diameter. It makes good sense because remember that anytime a line is tangent to a circle, then it meets the circle at a right angle, or it meets the radius of the circle at a right angle, and so does this one, right? And since these two lines have to be parallel, and they both meet at a right angle, that has to be a diameter. So a little bit of synthetic geometry there, some logic applying to the figure. So we have this line that's a diameter that's perpendicular to the line in question, or the two lines in question. And since we know it's perpendicular, we know its slope, right? Its slope is, down 2 and over 3. So this one has slope of negative 2/3. And that right away, for me anyway, opens up an idea about how I might solve this. I know that this line that's a diameter has this slope and it passes through the center of the circle, 3, -5. So I could find its equation because I have enough information to find what m and b are for that line. And once I find its equation, then I could use algebra to solve the system where I have the equation for the circle, the thing that we just finished up with, right? Take this equation for the circle and try to figure out algebraically its solution shared with the equation for the line. So that's the tact I'm going to take. And of course, it's not the only way you could solve this problem, but that's the one I'm going to try today. So let's find the equation for this line. I don't know, I'll call this line L. So equation for line L, it's of the form y = mx plus b, but I already know what m is. It's negative 2/3. So y = negative 2/3 x plus b, but I don't know the y-intercept. It looks to be about -3, but I mean, we can't trust the picture here, so I better go after it analytically. And the way that I do that is I can plug in an x and a y to solve for a b if I know one point that the line goes through. And the one point I do know it goes through is 3, -5. So let's do that. -5 is equal to negative 2/3 times 3 plus b. And 2/3 of 3, of course, is just 2, -2. And adding 2 to both sides will get me my answer is -3 is equal to b. So indeed, that line that's perpendicular to the two lines in question, that we think shares the same 2 points of intersection, has a y-intercept of -3, which looks consistent with the drawing. So y is equal to negative 2/3 x minus 3 is the equation for this line right here. So now that means that all I need to do is solve a system. The system I need to solve is y = negative 2/3 x plus 3, and the one for the circle, which we found in the last problem, x minus 3 quantity squared plus, I'm going to call it y plus 5 quantity squared equals 16. So we're going to solve this system. And solving a system is obviously finding ordered pairs that satisfy both of these equations. And of course, by the drawing, what we're looking for are these 2 points, right? Those are ordered pairs that are on the line and on the circle simultaneously. So let's go ahead and talk about how we do that. Now, you might be used to solving systems where you have 2 linear equations, something we teach a lot in high school, but this is a pretty rare case where we're solving a system that consists of a line and a circle, and a nonlinear system, I guess, equations. So this might be a little unfamiliar, but that's the whole point of these exercises, introduce you to some things in geometry you might have never done before. But the solution methods are really similar to what you're used to, right? One method that's really common, of course, is substitution. And I can see a nice, easy substitution would be to substitute this value, which is y, in for y right there, right? So in other words, if I know y is equal to this, I can plug that in for y here, and then I'll have this equation all written in terms of x, so it's one equation and one unknown, and we should be able to solve it, or we hopefully will be able to solve it. So let's go ahead and make the substitution. X minus 3 squared plus negative 2/3 x, and I called it plus 3, it's actually minus 3 there. That's going to be hard to erase, isn't it? Sorry, that's a minus. So So 2/3 x minus 3 plus 5, quantity squared equals 16. So that gets me to x minus 3 squared plus negative 2/3 x plus 2, quantity squared, equals 16. And now I can see right away I have a quadratic, meaning this thing's something x squared. This is going to be something x squared. Those will combine together. There'll be some like terms if I go ahead and double distribute both of these. And what it will give me is a quadratic equation, and we know that we have this thing called the quadratic formula that solves those, so that appears to be the route we're going. So x squared minus 3x would be minus 6x plus 9 would be the first double distribution. The second one would be 2/3 times 2/3, which is 4/9 x squared. Negative 2/3 times 2 is going to be 4/3. There's going to be 2 of those, so it would be negative 8/3 x, right? And then 2 squared is going to be 4, and that's all equal to 16. So now I'll add the x squared terms together. I get 1 and 4/9. Another way to write that is 13/9 x squared. And I have negative 6 and negative 8/3. So if I write this in thirds, it would be 18 of them. 18 and 8 more is going to be 26. So it's negative 26/3 x. And then let's see, I have a 9 plus a 4. So that's 13. And it's all equal to 16. If I subtract the 16 across, I get 13/9 x squared minus 26/3 x minus 3 equals 0. And I have a quadratic now in terms of ax squared plus bx plus c. We could use the quadratic formula on this, but you know, it's really kind of a nasty one, right? I don't want to really plug these fractions into the quadratic formula if I don't have to. And indeed I don't, right? I could just multiply by a constant on both sides, and since I have 0 over here, I will get just 0 when I multiply by a constant. So let's go ahead and multiply through by 9 on both sides. And when I do that, I get 13x squared, right? And then 9 and 3 will cancel. I'll get 3 times 26, which is 78 negative. And then 9 times 3 is going to be 27. And it'll be 0 on the other side. So now I have a nice looking quadratic. It's going to be a lot easier to work with in the quadratic formula. So let's go ahead and identify. This is my A, my B, and my C, right? And the quadratic formula works on any equation of this form. And its solution is given by x equals the opposite b plus or minus square root b squared minus 4ac all over 2a. Hope you like that rhyme. So let's take a look at it. So x is going to be negative b, so negative of negative 78 is positive 78. Plus or minus square root of, let's see, b squared is going to be, well, since it's negative, I'm squaring, it's going to be positive, so I'll just write it as 78 squared. Minus 4 times a is 13, and c is negative 27. That's nice because the negatives will cancel here. We'll get a positive under the radical, which indicates there are real solutions. And then it's all over 2a, so let's see, 2 times 13 is 26, right? So just a straightforward application of the quadratic formula. Now it's a matter of just simplifying these guys out. One nice thing I noticed is confirming my idea here is that we're going to get 2 x's out, right? And that makes sense, right? There should be an x for this point and an x for this point. So we would expect this to be a quadratic because we're getting two solutions. So 78 divided by 26 turns out to be 3. Ooh, that also makes sense, right? The reason is that we're going to have 3 plus and minus some value, right? So, and you can kind of see that by symmetry here, it's going to be 3 plus whatever this value is, and 3 plus whatever that value is, right? So it makes sense that the first number is 3 plus something minus something. That's going to give me my x coordinate for both of those points. Okay, so I did this on my calculator before getting ready, and 7,488 is what's under the radical, and that's all over 26, right? And then I looked a little closer at 7,488 and found out that it's divisible by 16 times 4 times 9 times 13. So that's what 7,488 is. And it turns out these three, of course, are all perfect squares, so they can be pulled out of the radical. So we get what, x equals 3 plus or minus. This would be a 4, a 2, and a 3. So 4 times 2 is 8 times 3 is 24. So we get 24. What stays in the radical is 13, and what goes on bottom is 26. And then, of course, 24, 26 can be simplified. So we get 3 plus or minus divided by 2. We get 12 root 13 all over 13. So there it is. Those are the two x coordinates. Let's go ahead and start a two-column version here. So let's call x1 3 plus 12 root 13 over 13. Let's call x2 3 minus 12 root 13 all over 13. And there it is. We found the x coordinates. We need to find the y coordinates, but we have an equation that allows us to find those, right? If we go back to the beginning, remember that we have this equation, negative 2/3 x minus 3. If I know x, I can plug it in and find y. So let's do that. So y is equal to, I just missed it, negative 2/3 x minus 3. Yep. Negative 2/3 x itself is 3 plus 12 root 13 over 13 minus 3. So let's go ahead and distribute the negative 2/3. When I distribute it to the 3's cancel and I get a negative 2. When I multiply it across to the 2/3 here, what do I get? I get, see, 12 times 2. Oh, here we go. The 3's will cancel, and we'll get a 4 here. And 2 times 4 is 8. So we get negative 8 root 13 all over 13. And that's my y coordinate, it looks like there. So 1 point, so this would be y1, x1, y1 could be written as 3 plus 12 root 13 all over 13, comma, negative 2 minus 8 root 13 all over 13. Seems kind of crazy, doesn't it? But let's just check it out and see if this makes any sense with the drawing. 3 plus 12 times the square root of 13 divided by 13. So here we get, so this is a rough approximation, 6.32. And then let's see, negative 2 minus 8 times the square root of 13 divided by 13. And we get negative 4.22. So if we go back to our picture, it seems like this point is this point right here. Negative 4.22. Oh, no, it doesn't seem quite right, does it? Let me pause here for a second. So I've decided not to cut this out of the video because I think it's instructive. I'd made a small mistake. You probably saw it as we went. And what was neat was that the decimal helped me pick it up. The problem was right here. I had a minus 3 that I forgot to bring down. And so in the y coordinate, I should have, instead of just minus 2, I should have minus 5. Does everybody see that? So it should be minus 5. And the reason this y coordinate didn't seem like it really made good sense to me. It seemed like it was in the wrong place. So now let's just try again just to see if this works. So instead of -2 beginning, I'll bring up my answer here again and just change it to -5. Hit enter. That looks better. -7.22. So now when I look at this, I can see that, yeah, indeed, this point looks like it's out sort of past 6 and change, right, in my x-coordinate, and down past 7, just barely past 7, which looks like it is in the y-coordinate. So x-coordinate 6 and change, y-coordinate -7 and change. Seems to make sense. So I'm more confident now I have that correct. Let's try this again for the other coordinate. Y2 is going to be -2/3 times 3 minus 12 root 13 all over 13, that whole thing minus 3. So we'll get kind of the same thing here, and the only difference is there will be a change of sign in the middle, negative times negative, so it'll be positive. -2 plus 8 root 13 all over 13, and then minus 3. And here we get what, -5 plus 8 root 13 all over 13. Boy, the other thing that's makes me feel good about this is that, again, I have the center of my distribution of the two y's at -5. So if I'm thinking up and down, I'm right here, and then I add and I subtract a certain amount for the y coordinate for these 2 points, right? So I add and subtract that. It looks like 8 root 13 over 13 to the -5. So just like in how the x-coordinate is centered at 3, the y-coordinates are centered at -5. Okay, so let's see, x2 comma y2 equals, I don't like my spacing here, so I'm going to give myself more room. It's going to be 3 minus 12 root 13 all over 13. Oop, no, comma. -5 plus 8 root 13 all over 13. And there it is. If I find what this is in an approximate sense, what we're really looking for is we think that this should be this point over here, right? Because we know that we've already found that point here. So let's go ahead and do this. Since I have the entry for the y sitting on my computer screen or my calculator screen, I'm going to re-enter it using entry, change that to a plus. So -5 plus 8 root 13 over 13. So this is a -2.78. And this one is going to be, let's see, 3 minus 12 times the square root of 13, all divided by 13. So -0.33. But of course, the two answers, I guess, if we were looking for exact answers, would be, this one and this one. And the two approximate answers would be these two. And that's the solution to this particular problem. Be neat to check it on GeoGebra, so let's do that right now. Certainly more involved problem than the previous two. So I guess the first thing we need to do is put in our equation for the circle, x minus 3 quantity squared plus what, parentheses y plus 5 quantity squared equals 16. There it is. And then what do we want to do? We want to find its center. So the center is this point right here. And then through the center, we want to put in the line that we decided was perpendicular to the two lines in question. It's that line. And by the way, you can change these lines into slope-intercept form if you right-click them and hit slope-intercept form. So -2/3 x minus 3 looks right. So then I'm going to put a point at the intersection here and a point at the intersection here. And of course, check to make sure that we have a perpendicular line there that passes through, or I guess draw in a perpendicular line. So there are two perpendicular lines. I think we've now got enough to sort of display what we have. So one thing I want to make sure is that both of these lines are of slope 3/2, and sure are, 1.5 and 1.5. So those are the two lines of slope 3/2 that are tangent to the circle, so that's good. And then of course here and here are the coordinates. So C, it's the one that we solved second, and negative 0.33 and negative 2.78 were the approximate values we got for that point. And the point D, which is this point in the lower right, is the first one we got, and that one's 6.33 and negative 7.22. Looks like I have a little rounding error on my handwork. I called this 6.32, but it should have rounded to 3.3, I guess, by GeoGebra's calculator. So looks like we're in good shape. I think we found them. All right, well, let's go back and move on to measurement. So skipping from analytic geometry to measurement, we use this term measurement basically to signify the study of quantity when it's applied to 1, 2, and 3-dimensional geometric objects using common units. So, things like inches or centimeters or square inches or cubic inches. So that's what I mean by common units. So length, area, and volume are examples of measurement topics in K-12 geometry. So let's take a look at a few of those. I have this handout that I thought would be fun to do today to show you a little bit about how I get the students I work with warmed up to measurement. It's called the area activity, and you can make a copy of it or just take a look at it on your computer screen. But here's what it looks like. Let's go ahead and talk it through a little bit. So this is what it looks like, and it's the way that I introduce area to students when I'm teaching it. And the reason I use this as an introduction, I mean, this is before we do any formulas, anything, is because I like them to get in the habit of thinking of area as parts and pieces, things that can be chopped up and added together or subtracted away. I tell them, they give them the simple directive that, look, this is 1 square unit, right? Work on trying to find the area of every one of the next, I guess, these 12 figures. And you can see that I've sort of sequenced them developmentally. I start with some simple ones, and then things get progressively more difficult. So let's do the front page together, and then I'll ask you to do the back page on your own. So what I like to do is watch what students do when giving this. Sometimes I'll see students subdivide, but most often students that I get who are preparing to be teachers will notice that this is, a 3 by 1, 2, 3, 4. So 3 times 4, 12 square units. I'm going to try to leave the space under each one. So this is 12 units squared. Here on this one, it's interesting to watch what students will do. Oftentimes they'll, make it into a rectangle and think about symmetrically about it, or using symmetry and think, well, this has got to be half of that rectangle. And in this case, actually a square because it's 4 by 4. So half of 16, it's got to be, so half of 4 by 4, it's got to be 8, right? 4 times 4 is 16, 8, yep, 8 units squared. But I will say that occasionally what I will see students do, they won't notice that it's half of a bounding rectangle. They'll just sort of do this thing, right? They'll say, oh, well, I've got a whole bunch of squares in here that I can just count, right? 1, 2, 3, 4, 5, 6. And then this is a half, and that's a half, so that's 7. This is a half, and that's a half, so that's 8. So I do see sometimes people thinking in unit-wise and counting half pieces. But that gets a lot harder down here, right? Because how do I count this little piece right here if I subdivide? So they have to think a little bit more carefully on this one. What I hope they see is that I can chop it here, right? And move this piece down here, right? And then get something that is 3 by 1, 2, 3, 4, 5. And so 3 by 5 is 15. And really what's going on here is they're learning before they even know it about the area formula for a parallelogram. This one, of course, is trapezoid, and lots of different ways I've seen different students handle this. Sometimes what I see them doing is chopping it this way and then taking kind of 2 pieces of area. So this piece would be half of a 2 by 1, 2, 3, 4, right? So half of 2 by 4, that's half of 8, so this piece has got to be 4 units in area. And then this is just a 3 by 4, so that's got to be 12. And 12 plus 4 is 16. Trapezoids are really interesting. We'll talk about that a little bit more in terms of thinking about area formulas. Here, things get kind of a little bit harder. Usually I see people do that first, and then sometimes I'll see them do this, and then think about these 4 rectangles, each of which is repeated twice. I like to think of it like this. It sits inside of a bounding box like this. And so what's kind of neat to think about here is that this piece is doubled there, 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 right? So that means I could just take the product 1, 2, 3, 4, 1, 2, 3, 4, 5, the product of 4 times 5, and take half of it. So this has got to be 10 units squared. And what that's really getting at is that the area of a kite, that's what this shape is half the product of the diagonals. Do you see that? This is a diagonal, that's a diagonal, and so half the product of the diagonal. Okay, then we go on to sort of irregular things, and I like these irregular ones because it really forces them to think about chopping things up. Really hard to have any sort of formulaic, easy way to find the area of this. But if we sort of think about, cutting things, and here one line, one smart line does it, that one works really good, because I know this is half of a 2 by 1, 2, 3, 4, right? So I guess this distance here is 4. So it's half of a 2 by 4, half of 8, that's got to be 4. And I know this guy is half of a 3 by 1, right? So that's got to be 1.5. And then this is half of a 3 by 3, so this has got to be 4.5. So 4, 5, 6, 7, 8, 9, 10. So 10 units squared is what we have to have here. And interestingly enough, these guys have exactly the same area, right? I think that's right. 4, 2 is 8, 8, 4, yep. That's a 3, and that is a 4.5, yep. 6 plus 4 is 10, yes. Okay, so I've given you, I guess, a warm-up. Here's your challenge. Let's ask you to pause the video and to work these ones on your own, and then when you start the video again, I'll go ahead and share with you my solutions. So let's go ahead and pause it right now. Okay, hopefully you paused and took some time to work these on your own. Here's my solutions. Of course, I'll scan these and make these available as handwritten notes to this lecture, but I'll quickly go through each one and let you know how I thought of it. I think this one's a really hard one to start with. It's sort of, in retrospect, I almost feel like it should belong down here because it's pretty hard to do without using a subtractive method. So the way that I did it is I said, well, there's a bounding box around the whole thing that's 5 by 5, so that's 25 square units. And what I need to do is take away all the white space from that 25 square units to find out what the dark space is. And the white space is easier to calculate from my standpoint than the dark space is. So what I did is I took this rectangle, calculated its area as 5 square units. This square is 9, it's a 3 by 3. Here's a 3 by 2, but it's a right triangle, so it's half of 6, so it's 3. And then this guy is a 5 by 1 in terms of base and height, so that's got to be a 2.5. When I take all this white space away from the area of the whole square, I get 5.5 units squared for dark space. This one I found pretty easily by subdividing right here. Kind of reminiscent, that one is kind of reminiscent of this one. I don't know if you feel that, but single line subdivides into countable spaces. It is a little bit harder to see though that this triangle here has a base of 1 and a height of 2. It's an obtuse triangle. They're notoriously difficult for students to find the area. But 1 times 2 divided by 2, that's going to have area 1. This is 1 by 2 divided by 2, that's area 1. Interestingly enough, those two triangles have exactly the same area. 1 plus 1 plus 6 gives us 8. This one I used a combination of two different tactics. I directly calculated these two areas. I see this as a base of 1 and a height of 3. So 1/2 1 times 3, that's 1.5. This one has a base of 1 and a height of 2. So 1/2 1 times 2, so that's just got an area of 1. So 1.5 and 1. This little piece here, what's left over, I found difficult to calculate using a subdivision, I guess by dividing it up. So what I thought to do instead was to put it inside a square, a 2 by 2 square, and subtract away the white space. So the 2 by 2 square is 4, and then this triangle is half base times height, 2 and 1. And this triangle is half base times height, 2 and 1. So you end up subtracting away 1 unit here and 1 unit there, and you end up with 2 square units here. So it's 2 square units for this, 1 and 1.5, so it's 3, 4.5 square units for the whole thing. This one I did similarly to this one, but symmetry really helps you here. If you draw the big bounding box and then draw in some extra helper lines here and here, this of course is a 4 units. This is 4 units then by symmetry. This one I found to be 3 units, so all the other ones are 3 units by symmetry. So 25 minus 3 times 4, which is 12, minus 2 times 4, which is 8. That's 25 minus 20, so this guy's 5 square units here in the middle. Let's see, the last two, I did a smaller bounding rectangle. It was a 4 by 5 bounding rectangle, so I start with 20 units, and then I subtract away 2, 3, 2, and 2.5 square units to get to my answer of 10.5. And then this one as well, I did a large bounding box and subtracted away parts and pieces. I subtracted away 2 for here. I subtracted away 2.5 for here, and 2.5 for here, and 4 for up there, and it turned out to be 14 square units is what I got for that particular one. So I really liked starting this conversation of measurement by confronting the whole, I guess everything that you can imagine in a simple sort of setting, and especially in a setting where you can compare, right? You know that none of these are going to be bigger than what, 5 by 5, 25, right? That's as big as sort of space we have, and I think that's really good. Kids start to sort of see things as making sense. This guy's got to be smaller than that guy, for example, just looking at how much area is covered. And it's not a big surprise to me that this is the largest area on the page here, and a close second here. So I think it's a really interesting way to start it out, and it helps them, I think, when we get to this point of sort of deriving formulas, which is where we'll go next here. Let's see. So let's derive the formula for the area of a trapezoid using the fact that the area of a triangle is 1/2 the base times the height. Okay, so you've probably seen this derivation before, but let's just make sure that we're all on the same page, because this is what I'm going to use to teach your GeoGebra lesson this week. So if we draw a general trapezoid, something that looks like this. Let's see, there's, I don't know, maybe something like that, and something like, so I don't want it to be an isosceles trapezoid. I don't want it to be the special case. I just want it to be a general trapezoid. There it is. We know that if it's a trapezoid, it has to have at least one pair of parallel sides. And usually what we see happening here is that this one is base 1, and this length down here is base 2, or vice versa. And then this distance between them, this distance between the two parallel lines, which I always like to draw out here, is called the height. So the perpendicular distance between them. And what we want to show is, why is the area of a trapezoid equal to 1/2 base 1 plus the base 2 times the height, right? So now we're getting into this sort of reasoning and generalization sort of area of measurement. And the first thing I notice when I think of this formula is that these two bases, when I add them together and divide by 2, what I'm really doing is averaging the bases. I'm finding a number that's exactly between these two numbers, and I'm multiplying that by the height. And that sort of makes sense, because if I chose base 1 and multiplied by the height, that would be too small, right? Because that would just give you that rectangle in there. And if I chose base 2 and multiplied by the height, that would be too big because that would give you this rectangle here, right? Just loosely drawing it. So it makes sense that it should be some number in between base 1 and base 2 that I'm multiplying by. And it turns out that the right number is the average of these two bases, and multiply that by the height. So the big question is how can we show this is true by using triangles and the area of triangles? And usually we've studied triangles before you study quadrilaterals, and so it's a good thing to rely on if you can. And here's the idea. The only way we can make triangles out of quadrilaterals is by connecting up two opposite vertices. You connect these two, or you could connect these two. It doesn't matter which. But now I can see that there's sort of a triangle 1 and a triangle 2. I'll just sort of label them that way. And if I think about the area of the trapezoid, well, it's got to be the sum of these two, right? The area of triangle 1 plus the area of triangle 2. And triangle 1 is this one up here. I know the length of its base. It's base 1. So it's base 1. And then the question is how high is the peak above the base? You kind of have to think of this upside down, but if this was the base, then this would be the vertex by which I'm measuring the height. And we'd have to extend the base out here and think about this, right, as the height. And of course, that's the same thing as this height, right? So it's B1 times h divided by 2 for this triangle's area. And similarly, if I think of this triangle, T2, it's going to be 1/2 base 2, this base, times that height right there, which is the same, of course, as the height that separates the two parallel lines in the trapezoid. So B2 times h. And now I can see I'm dangerously close to the formula. The only thing I really need to do is factor out of these two, I guess, algebraic terms, like terms, and I see a 1/2 h comes out of each. And what's left inside is B1 plus B2, and a little bit of commutation then gives us what we're after, which is 1/2 B1 plus B2 times h. So here's our derivation that relies only on the area of triangles, and of course we can do this for any trapezoid, right? So it passes this, I guess sufficiently general test. Anytime I have a trapezoid, I can triangulate it. I can find the two triangles. One will have this base, the other will have this base. They will both have the same height. And so this derivation works for any trapezoid on the planet. That's kind of neat. All right. Oh, I'm sorry, there was some, I don't know why it does this. Sometimes it wants to write. So let's do a little bit of GeoGebra instruction, then I'll quit. I'm sorry this lecture is going a little longer than normal, but when we have help students to see generalization, which is one thing a lot of you mentioned in the first week of having something that you would like to do more of in math class, and I think GeoGebra would be a place you could turn to help kids generalize. This is when we're doing things like deriving formulas for the area of a trapezoid, or deriving formulas for the equation of a line, or deriving formulas. We do this a lot as math teachers, and we'd sure like them to tell us what those those formulas are instead of us have to tell them. And I've found that GeoGebra can be a powerful tool to help students see these formulas. I mean, the dynamism itself helps them to sort of generalize it, to see that it's universal, that it works for any trapezoid in this case, let's say. And then you can use these check boxes, right, to add or subtract these helper lines, these things that you hope somebody says, hey, add a line to the diagonal, and then you can show it. But if they don't, then at least you've got it preloaded and you're ready to go, and to help them see something. And then one thing that I think is really neat is you can reverse things. If you have a dynamic area calculation, you can say to kids like, what should I do to make this trapezoid have an area of 25? I think those are always really powerful types of questions, because then you can basically see, if they understand the concept by reversing the concept. I have this area, you give me a trapezoid of certain dimension, and then of course GeoGebra will let you check it, which I think is a really powerful action. A lot of the research says that reversibility, if you can reverse a rule or a procedure, that's a real true sign of conceptual understanding. So something just to keep in the back of your mind, that GeoGebra can sometimes help you practice reversibility. So to practice this, let's build a GeoGebra tool that helps students understand the two-triangle derivation of the area formula for a trapezoid. So just what we did on paper in a static sense, let's build something that might help students understand this derivation if we were really teaching it. So let's go ahead and open GeoGebra and build something that might be useful in teaching students about area. So one of the things I would do right away is I'd leave the grid, but I'd get rid of the coordinates. I'd build a trapezoid, a general trapezoid. So I'd start with the first base, and then I'd put in another base, but it's got to be a parallel line, right? So what I'll probably do is I'll put a point up here, and then I'll build a parallel line through that point. If I hover over it, it says select a point and a parallel line. So I'll select this point and this parallel line. There it is, another a line parallel to this base. And what that does is allows me to play around with trapezoids that aren't necessarily have horizontal bases. So then what I'll need is I'll need another point on that line. So this would be base 1, that would be base 2. And then I'll complete my trapezoid. There it is. And then I'll probably hide this line. And now I have a general trapezoid, meaning that I should be able to sort of, and do you notice how those two lines stay parallel always? So I could drag it out horizontally or drag it in. And the other thing that's nice is that I have the ability to change the length of the two bases. All of these would be trapezoids, of course, including a parallelogram, right? They have at least one pair of parallel sides. Okay, so we've got the trapezoid, and by the way, it tells us what the area is right there. It's 60. So let's see what we have here. Let's go ahead and put in some things that you would need, and then what we'll do is we'll use checkboxes to take them away. So let's go ahead and measure some distances. One distance we're going to want to measure is this, CD. Another distance we're going to want to measure is this, AB. And then what we need also is we need a perpendicular distance, a height right here. So this is going to be interesting. How should we do this? If I put the line back in, what I'm going to do is I'm going to put a point, a perpendicular line. Oops, there it is. I'm going to put a line through B perpendicular. That gives me this point right here. So now I'm going to hide both of these lines, and I'm going to put a segment in here, and I'm going to measure its length, and it's 6. And then I'm probably going to change the way it looks, just because I want it to be sort of like a dotted line, like a helper line. And then maybe what I do is I add back in this line and make this line a dotted helper line too. So something like that. The reason I did it this way is because, I'll hide that piece. The reason I did it this way is because this will allow me to sort of do anything I want, right, to the trapezoid, but still gives me a nice way to measure the distance between the two lines. So right away you can see, that the average of 8 and 12 is going to be 10. 10 times 5 is 50, and 50 is indeed the area of the trapezoid. So that's kind of nice. You can see the way this is working. But what we kind of want to do is we want to show them the area of two triangles that also comprise parts and pieces of. So let's go ahead and measure area. There it is, area. There they are. Okay, getting close here. And the other thing I want is I want the area of the trapezoid, which I guess I already have, but I'll put that in a dynamics text box here below. So I'll just say area of, I think it's ABCD, ABD. Oh, I don't like the way, we'll change it. ABCD is going to be this number, quadrilateral Q1. So this is objects and Q1. Hit OK. There it is. Get my pointer tool back. Make that kind of bigger. Let's say large. Something like that. So we can see 50 is 20 plus 30. And we have this sort of a picture now. So now we can kind of put some check boxes in to help us out. So I'll go ahead and put a checkbox in, and the first thing I'm going to put it in as is how about show, let's say, height. And what I want to put in there is I want to put this line in, and that distance in. Let's see, I'm trying to see if I think that distance is just attached to the segment. So let's go ahead and hit apply, see what happens, and get my pointer tool. Yeah, so that just basically shows them the height of the parallelogram, excuse me, the trapezoid. Let's go ahead and do another checkbox to say how about show triangles. And there what I want to do is these two triangles. I clicked on them, hit apply, and then I want to do one that might include the triangle areas, because maybe, you know, maybe kids, once they see the triangles, they'll be able to see that the two areas work like they do. But let's do show triangle areas, and the two areas are 20 and 30. Okay, apply. Let's see how that's all working. So now if I take away the triangles and triangles area, ooh, the show triangles, I think I'm just going to get rid of this segment. I don't think I need it now. Let's see here, get rid of those segments. Let's see if show triangles, oop, I broke it, didn't I? Okay, so I've got to redo that. Actually here, let's do it this way. I'm trying to bring it back in. Okay, so triangle areas works, but show triangles doesn't. That's just the triangles, so I need to edit this one. Object properties for show triangles. Maybe I'll just get rid of that one. So this one I am going to delete, and I'm going to redo it this time. Let's see here if I can get it right. So show triangles, and I want this triangle, that triangle, and this segment. Let's see if that works this time. Sure didn't, did it? And maybe the segment is in there twice, so I'm just gonna hide it, just get it hidden for sure. There we go, now we're looking good, and the areas can come in and out. So now I guess the last thing I would do would be show bases, and put that maybe above there. So if I show the bases, then what I want is I want that and this guy, apply those, and so there it is. I think now we have enough to at least sort of think of it as an object that might help students understand the area formula. Usually what I do is, I don't know, I unfix all of these, so I hit fix, unfix them. So I'm right clicking and and unfixing them, and then I put them sort of right up above and below each other here, and these on the grid sort of makes things nice. And then, oops. So all of those now we can fix them. So now you can't change them. Show triangles, show triangle areas, show the height, and show the bases. And now we have something that, of course, you could use to teach students this idea. And once they understand the idea, what might be really fun, I think anyway, would be to ask the students to propose. I've given you an example here of something with 70 as its area. Can you propose a trapezoid that has area, I don't know, let's say 80? I mean, what would you do to change this to 80? And what would the bases have to be? So you could bring the bases in and think like, okay, one way you could do 80 is you could do 8 times 10. And if 8 was the average of the bases, then the sum of the bases would have to be 16. So 8, 12 plus 4 would make 16. So that would work. And then, so that would work to make the average 8. And then the height would have to be 10 then. So I would have to actually move this guy down 3. 1, 2, 3. And this guy down 3. 1, 2, 3. Oh, and this guy has to come back to 4. And there is 90. Oh, because the 14 has to become a 12. And this has to stay at 4. There it is. I got it. I got a trapezoid of area 80. So it'd be really interesting to see if students in your course, given something like this, could reverse this idea of area once they understand the formula. And hopefully this piece of technology would help them see that these two triangles, of course, are the magic way of sort of justifying why 1/2 base 1 plus base 2 times height. All right, I've certainly spoken long enough today. I'm sorry to keep you for 20 minutes longer than I usually do, but I hope that it has given you some ideas about how you might use GeoGebra to help kids see mathematics dynamically and perhaps reverse some of the processes that we teach them to check for conceptual understanding and awareness. All right, well, let me know if you have questions, and good luck on your content exercises this week.